Okay, good morning, guys. Uh, we'll start the introduction to quantum mechanics. As you know that the light has got two phases, indeed two natures. The first one we call it as a wave nature, and the second one is called as particle nature. So quantum mechanics is based on the particle theory of light. So if I draw a photon, I will draw a circle, and with a line that is the sphere here represents that it's at a particle, and the wave here, this curve here represents that's a wave. So indeed, the photon has got two faces, as we know it. That's the particle-wave dualism or duality. The particle or light particle is Einstein proposed. Einstein proposed, that the particle, a small particle, the light particle has no mass at rest, and it has got no charge. So let me write that Einstein proposed that a light is composed of tiny particles that are known as photons, which have no mass at rest, and no charge. So the first, definition for the photon or light particle was given by Einstein. And of course, it was continued by several scientists, and the scientist that was given and calculated the energy of a photon was Max Planck. He has done it in 1900. He proposed that and derived the formula for the energy, the tiny energy, small portion of energy that then can be calculated by h times nu, whereas the h is called as Planck's constant. And h equals 6.63 10 to the power of minus 34 joules times second. And nu here is known as the frequency of light. When we try to calculate the, for example, total charge of any charge, of a given charge, of course, the smallest value that we can obtain is the charge of electron that we know that is 1.6 times 10 to the power of minus 19 coulombs. So any kind of charge can be calculated in this way. So any kind of energy that is brought by a light wave can be calculated as the portion of small energy that can be calculated in this way. And of course, the energy is measured in joules, where the frequency, or I will denote it by nu, and nu is denoted by hertz, is measured in hertz. And I've already given, or it can be rewritten by 1 over second, or second to the power of minus 1. And the energy here, the amount of energy, is called as quantum. So that's why the physics that we try to cover we'll call it as quantum mechanics. By the way, the plural form of this is quanta. Max Planck derived the formula for the energy that is known as energy of a photon or quantum. Let's suppose that I have, for example, I have the frequency of a particle that is given as 1.5 times 10 to the power 15 joules, hertz. Hertz, that's the frequency. If I try to calculate the energy, as we mentioned before, h times nu, that's 6.63 times 10 to the power minus 34, multiplied by nu, that is 1.5 times 10 to the power 15. Of course, the energy can be calculated. First of all, we have to deal with the powers, and the power is 10 to the power minus 19, and the number that is obtained by multiplying 6.63 by 1.5 is 9.94 joules. So the number is very small, 9.94 10 to the power minus 19 joules. So that's why we have a special unit that's known as electron volts. Electron volts. 1 electron volt is 1.6 times 10 to the power minus 19 coulombs, or joules, sorry. So you see here that it's similar to the charge of electron. So that's why if I try to express it in electron volts, I have to divide by 1.6 times 10 to the power 19 this value, and I obtain 6.21 electron volts. So that's another unit for the energy. Let me write it here. We have two units that can be used for the energy of a photon or quantum energy, that is joules, and of course electron volts. But electron volts are more convenient to calculate. And now suppose that this energy also can be rewritten, since I know that lambda equals speed times the nu here, the frequency, speed over frequency, or let me write it in more convenient way, speed over frequency, because you know that speed is measured in meters per second. If I divide it by 1/second, that's the same thing as multiplied by second, and I'll get the meters. So that's why the wavelength, if I try to derive it in terms of speed of light, because I know that the light moves with the speed of light that's denoted by c over nu, and the formula of that was derived by Planck tells me that it's h times nu. So instead of nu, of course, I can write c over lambda. So if I just plug it into the term of nu, I will have the new formula that is h times c over lambda. So the another equation for the quantum hc over lambda, where the lambda is known as the wavelength, and c is the speed of light, that equals 3 times 10 to the power 8 meters per second. So the wavelength can be measured in nanometers, in meters, in micrometers, anything else. So suppose that, for example, for simplicity, I have the wavelength of a light wave that is 400 nanometers, that equals 400 times 10 to the power minus 9. It means that it's 4 times 10 to the power minus 7 meters. So what will be the energy carried by this amount of light, by this color indeed? Energy can be calculated as h 6 times 63 times 10 to the power minus 34 times speed of light, 3 times 10 to the power 8, and over 4 times 10 to the power minus 7. This goes upward with a positive sign, this minus 7. When it goes to upward, it will change its sign to a positive, so minus 34 plus 15. Again, it gives me 10 to the power minus 19. I deal with the powers first of all, as you see, and 6.63 multiplied by 3 and over 4 will give me the number of 4.97 times 10 to the power minus 19 joules. As I mentioned before, that will be more convenient if I express express it in terms of electron volts, so that is 3.1 electron volts. So that's the energy carried by 400 nanometers a light particle, and it can be easily calculated, you see. Okay, we've solved a similar example. I will give it to you. You'll try to do it your own. If you see this video, try to find the energy of a photon by your own, because the previous example was the same. And another thing that can be said about the photon also as a light particle, since it's a particle, it has got its spatial momentum. Sorry. Okay. Momentum here. Right. Okay, let me write it here. Every particle has got its own momentum. And you know that the momentum, indeed, that is, if I try to write the formula for momentum, it's a vector quantity, you know, and that is m times c. Indeed, that's the momentum is m times v, but since my particle moves with the speed of light, I can write it as m times c. How can I get the mass here? The most important thing is to derive the formula for the mass, and I know that the most famous formula of Einstein, that was derived by Einstein, is E equals mc squared. And on the other hand, I have that is equals energy equals hc over lambda. So I can write here, since these two are equal, mc squared equals hc over lambda. I can simplify one of the c, and I can write that the formula for mass is h over lambda times c. So if I plug this expression instead of mass here in a momentum, I'll have that the momentum equals hc, yes, over lambda c. You see here that the c is simplified, so h over lambda, let me write it in more convenient way, h over lambda will give me the momentum of a light particle. And the unit for momentum, as we see in the formula here, that is kilogram times meter per second. So the momentum can be measured in kilograms per momentum. Kilograms times meter per second, sorry. This formula was derived by James Maxwell. And suppose that I have, for example, as in an example given, I have a momentum of photon of wavelengths of a given wavelength. The formula for momentum is h over lambda, where the h is 6.63 times 10 to the power of minus 34. I will divide by 6.63 times 10 to the power of minus 7. I simplify the numbers because they're exactly the same. And this power goes upward with the positive sign, and this minus 34 plus 7 will give me 10 to the power of minus 27 kilograms times meter per second. You see, it's pretty easy. I've especially chosen this example because the number was very convenient for me. The next guy here is Louis de Broglie. Louis de Broglie, French scientist. Sorry, de Broglie. He derived the formula for the wavelength that is known as de Broglie's wavelength. So what is it? As we mentioned before, we derived the formula for the momentum, as we mentioned, as h over lambda, and on the other hand I have the mass times v. So these two are equal. I can write as h over lambda equals mv. So that's why the lambda can be obtained as h over mv. What does it tell us? That's called as wavelength, indeed de Broglie's wavelength. De Broglie's wavelength. French scientist de Broglie proposed that any particle sometimes can behave like a wave, so its wavelength can be calculated by this formula that is h over mv. It's known as de Broglie's wavelength. Suppose that, as an example it's given, a proton traveling with the same speed of 1.6 times 10 to the power 6, and the mass of electron is given. So I'll have here that calculate the wavelength of an electron and the proton traveling in the same speed of 1.6 times or 1.0 times 10 to the power 6. So we'll try to find the lambda for the, first of all, let me find only for the electron, and we know that it's h over m of electron times its speed. I know that 6.63 times 10 to the power of minus 34, I will divide by mass of an electron, that's 1.11 indeed I use, times 10 to the power of minus 31, and the speed, that is 10 to the power of 6. So this here, if I deal with the powers, first of all, I will have here minus 3, and this goes upward with the minus 6, so that will be 10 to the power of minus 9. So 6.63 over 9.11 will give me 0.73 times 10 to the power of minus 9 meters. So that's about 0.73 nanometers. So electrons, it means that the electron sometimes can behave like a wave, which have the wavelength of 0.73 nanometers. So this equation was derived by de Broglie. Keep this in mind, please. So we covered today some of the quantum mechanics basics, fundamentals. The first one that you have to remember that the first thing that you have to keep in mind let me write here. The first thing that you have to write, that you have to keep in mind is that the first definition for the photon, or the name of photon, was given by Einstein, and then the Max Planck derived the formula for the energy of photon. Then we derived the formula that James Maxwell was derived for the momentum. of a light particle, and also we've derived the formula of de Broglie's wavelength, de Broglie, and that's wavelength. These are basic concepts. They're related to quantum mechanics introduction. I hope that you understand it. Thank you very much.